linear field, and then it gets the total field. Then you can differentiate the field and get the stuff that you want: force, acceleration, those kinds of things.
Okay, so the order of the calculation has to be this way, right? So it has to be do the multiple expansion and then translation and then local expansion, because otherwise you would not have the data for the local expansion.
That is correct. That is correct. The multiple expansions are used in computing translations, and then the translations are used in computing the local expansions.
Mm-hmm.
Okay. All right. Okay. Let's go to the next slide, which is where we get to the integer representation of the cells. I think you probably know this, so I would like to go over this very quickly. Just look at the geometric picture to the left, and not the tree for now. So again, this is 2 dimensions, and we have x and y. So we are talking about boxes at various levels, right? So the whole domain is one box, and you can think of representing that with an empty string. Then when you break that into 4 sub-boxes, you essentially need to have 1 bit along x and 1 bit along y. So you use the red stuff. So you look at the red bits, the 0 and the 1 for x, and the 0 and 1 for y. So together they determine the 4 boxes at that level. So 0, 0, 0, 1, 1, 0, and 1. And to give a label to a box, you simply take the first x bit and then the first y bit, the second x bit and the second y bit. So you do bit interleaving. Okay. So the bottom left red quadrant is the 0, 0 box. Then the bottom right would be x is 1, y is 0, so it would be 1, 0, and so on. Okay. So the bottom left quadrant is the 0, 0, and the top left is 0, 1. So you can actually draw a line from 0, 0 box to 0, 1 box to 1, 0 box to 1, 1 box. And you will see that what you get is exactly the z-space filling curve or the Morton ordering. So that's how the z-space filling curve or Morton ordering is related to orderings. Okay. Now at the next level of boxes, you have 4 along x and 4 along y. So use bits. So you have 0, 0, 0, 1, 1, 0, 1, 1, the blue ones, the x, and similarly on the y. And then again, you can form boxes by interleaving the x and y bits. And in terms of the tree, what we do is that because we simultaneously have to deal with cells at multiple levels, we prepend every bit string with a 1 so that you can distinguish between 0 and 0, 0 and 0, 0, 0. Okay.
Srinivas, I actually missed the ordering part. Can you just like the beginning of it, the bottom and the top, is that something?
Right. Which did you miss?
The Z ordering. I just want to.
Okay. So the Z ordering or the Morton ordering is an ordering of points in space. Essentially, you have points in multidimensional space, and you want to impose a linear ordering on them. The Morton ordering is a way to impose the linear ordering, and it's called a space filling curve because if you take the points, you actually select them in the order in which the Morton ordering orders it, you would get a non-self-intersecting curve, and that's why it's called a space-filling curve. So a space-filling curve is a curve that fills space and doesn't intersect itself. You can think of it like a snake can, arrange itself according to a space-filling curve. Okay, it's simply a non-intersecting curve that can fill up space as much as you like based on a rule. Okay. So the z-space filling curve or Morton ordering is obtained by interleaving the x and y bits. And that's the same thing we are doing in building this arc-tree and naming the cells in the arc-tree. So essentially, the left to right order of the leaves in the arc-tree is exactly the same as the Morton ordering.
So let me try to understand when you say left to right ordering. So 0, 0 will start at the leftmost leaf.
Right.
And the rightmost leaf is? Well, ones.
Yeah, so you list the children of the node, then 0, then 1, 0.
Okay, but how about the non-leaf nodes?
This would work actually at every level, but the points are only at the leaves, right? So if you order the leaves, it's the same as ordering of the individual points. And Morton ordering or Z space-filling curve is mentioned about only connecting the points, and therefore we only talk about the leaf.
So in other words, in the numbering, you don't actually consider the parents. You only consider the leaf nodes. But the thing is that I see numbers on the parents.
Can you go over that again?
I said in the ordering, you only consider the leaf nodes, right? In the space filling curve, you're only traversing the leaf nodes. But I see that you have numbers on the parents as well. So how do you get unique IDs for the parents?
Okay, so that's what I'm talking about, is cell decomposition of the space. So if you look at nodes at any particular level in the octree, again, for simplicity, let's not go to compressed octree right now. We'll just look at octrees. So all the nodes at any level in the octree correspond to boxes of the same size. And you can think of your domain as decomposed into boxes of that particular size. And then the number of boxes along any dimension would be a power of 2. Right? You would have either 2 boxes or 4 boxes or 8 or 16, stuff like that. So simply use as many bits as needed to represent each dimension, to differentiate between the boxes. Right? So now every box will have an X coordinate and a Y coordinate. You simply interleave the bits and you will get the box D as a bit string. And then you put a 1 before that bit string.
You put a 1 because the root is 1, right?
No, you put a 1 so that you can distinguish between boxes at different levels when you are using the bit representation in a computer. For example,
yeah, that is correct.
One way to store 00 and 0000.
Yeah, that's the same thing.
While maintaining,
so you have to have 1.
On a piece of paper, I can write 2 zeros and 4 zeros. These are different. But when I put 0 in a 32-bit word, I have 32 zeros there.
Right. So the only way to construct this is always have the root to be 1, right? So.
Yes. So essentially, the 1 is just to distinguish between so root is empty. So when I put 1 before something empty, it just becomes 1.
Okay.
Left child is 00. Okay. And it becomes 100, and the left child of that is 4 zeros, and that becomes 1 followed by 4 zeros. So that when you store them in an unsigned integer, you can differentiate.
So are you assigning these numbers when you're constructing the tree, or like this could be assigned like top down, right? You can just assign the root.
Yeah, actually, the tree itself is constructed by using these numbers intelligently.
Oh, okay. So it's part of the construction of the tree instead of the other way around.
Yes.
I see.
So, Shri, just so I understand, like, how do I distinguish the red node on the right, 111, from one of the leaf nodes that's going to have the same representation?
You will not have the same representation. Because the length of the representation is a function of your level in the tree, right? So the root has 1 bit. The next level, everybody has 3 bits. The next level, everybody will have 5. And the next level, everybody will have 7 bits, right? Because
so let me. Okay, I think I got it. I think basically the leaf node you're saying is always going to have its leftmost bit 1. Because it has the leftmost bit 1, you know how many bits to consider.
Right, exactly. Right. So what I do is when I look at an unsigned integer, I must look for the leftmost 1 bit. And that tells me the remaining bits where I should start looking at, essentially, that's all.
But without knowing the tree, how can you construct the names?
The way this works is the following. You can directly compute, so in many of these applications, So there are two ways to look at it. One is that you may specify the highest resolution that you permit. In other words, you say my leaf box has a certain minimum side length. I'm not going to go break below that. Even if the box has multiple points, that's fine. I'll deal with them directly. I don't want to subdivide below a certain point. Now, there's a good reason why you want to do that in many applications. For example, when I build computational electromagnetics codes using FMM, there is a certain minimum size required for a leaf box. Otherwise, your computations will not be correct. And therefore, that serves as a natural stopping point, irrespective of whether that box has one point or multiple. Now, there is another way to compute this. You can, as I showed, I think a couple of meetings before, if I take the XYZ coordinates of a point, then if I know the minimum side length of a box, then I can, so let's say that D is the size of the domain, and the minimum side length of a box is going to be D divided by 2 to the power L, which means that the height of the tree is L. I'm not going to break more than L times. Okay? So then you can divide your X and Y and Z coordinates separately with D by 2 to the power L and take the floor of that, and that gives you an integer number, right? So think about it this way. It's very simple. You look at the domain, for example, okay, and focus. Okay, so now there are red lines, there are blue lines, and there are brown lines, brown dotted lines, right? So let us look at only at the red lines and take away everything else from our mind. Then you have the domain, you have the horizontal red line in the middle and the vertical red line in the middle. So when I'm thinking about boxes of that big a size, I have only 2 boxes along each dimension. So I can use 1 bit to differentiate them. 0, 1 on the X side and Y, 0, 1 on the Y side. When I go to the blue level, then I have 4 boxes along each dimension. Think of only the blue lines, right? So the red line is also, you have to think of it like a blue line, unfortunately, because the blue line is there in the center too, but it's overwritten by red. Okay? So now consider both blue and red lines. Okay? Taking them together, you're breaking the domain into cells of a particular size, and there are 4 along each dimension. So you need 2 bits, 0, 0, 0, 1, 1, 0, 1, 1, right? And if you go down to one more level, now you have these brown dotted lines. Now you look at every line in this domain, brown, blue, and red. And now you have 8 boxes along each dimension, and you can write them as 0, 0, 0, 0, 0, 1, etc. along X, and same along Y. Okay. So essentially, if you know the size of a leaf box, that's all you need to know. Then you divide the XYZ coordinates of a point separately with D divided by 2 to the power L, and take a floor of that. That gives you the number of your box along X, Y, and Z. And then you can turn that number into a binary number and then do a bit interleaving, and you directly compute the identity of the cell. Okay? And once you compute that, then your construction algorithm will automatically construct internal boxes and things like that.
So what's the complexity for this thing? You have to go.
Reconstruction would be n log n for compressed dot trees.
I see. Yeah, that's correct.
Okay. And basically, there are some nice tricks that one can do, right? If I have the bit strings corresponding to 2 cells, and I ask you, suppose those 2 cells are siblings, and you want to know their parent, right? You don't even need to know your sibling. If you want to know your parent, simply knock out the rightmost D bits if you are dealing with D dimensions, right? For instance, let us look at the leaf node for which the bit string is written in this diagram, which is 100110. Okay, that's 7-bit string, which is right to the left of the leftmost brown node at the bottom, right? Now, if you want to compute its parent's ID, you simply remove the rightmost 2 bits, right? And its parent would be 10001. If you want to compute the parent of that, you remove the rightmost 2 bits. Right?
So what if you have a compressed node there?
Yeah, of course, you have to deal with these things differently in a compressed rock tree. But in a regular rock tree, it's very simple.
Oh, yeah.
Right? If it's 3 dimensions, you knock out rightmost 3 bits, you get your parent. Knock out another 3 bits, you get your grandparent, on all the way up to the top, right? So your representation consists of 3k plus 1 bits if you are at depth k.
Is that the same thing for a compressed rock tree?
Well, for a compressed octree, you may lose 3 bits to go to the parent, may lose 6 bits, may lose 9 bits, but you lose a multiple of 3.
I see. Do you just simply knock out the bits and see whether there is a node that looks like that? If not, then go one more level, just knock out 3 more bits, stuff like that?
Yeah. Okay. So there is a key property here. So if I give you 2 arbitrary nodes in the octree, and I want you to compute their lowest common ancestor, okay, which is start from each of those nodes, walk all the way up to the root. Obviously, these 2 paths will somewhere intersect somewhere, at least at the root. So wherever they meet first, that's the lowest common ancestor, right? So there is a very crucial property which can be very nicely exploited. So if I have the tree, I can give you 2 nodes and ask you what is the lowest common ancestor. You can actually traverse up the tree and find the first meeting point and say that node is the lowest common ancestor. Now there is a very nice property by which you can compute it geometrically. Okay, what you do is you take your bit representation and you take the bit representation of the other node and see between these 2 strings what is the longest common prefix. How many bits do you agree on, right? You will certainly agree on the leftmost one. You will agree on bits in groups of 3, up until some point. And at some point you start disagreeing. So throw away everything when you disagree. And that prefix gives you the identity of your lowest common ancestor.
Yes.
So you can compute the lowest common ancestor in this tree in constant time geometrically and not bothering with the tree. And this property is exploited to come up with a construction algorithm for the tree. Okay. I think you're doing a great job of following. It's just that I'm trying to present stuff that probably belongs to half a dozen papers or so in one talk. So, but from the questions you're asking, I can see that you're understanding it quite well. It's just that there's a lot of stuff I'm throwing at you in just 1 hour, and so if I do a good job, then maybe some of it will remain in your memory after. Okay, can I move to the next slide?
Yes.
Okay. So for tree construction, again, I'm going to describe parallel algorithms from this point. I'll assume the existence of sequential algorithms without talking about them, just to save time. And if needed, I can either send you a paper or I can give you a talk at some point. Okay. So here is the parallel algorithm for tree construction. One thing that I learned is that I would like to construct the trees and store them not as trees, but in an array in the post-order traversal of the tree. And that has lots of nice properties, and it gives me very nice parallel algorithms. Okay? So the first thing that I would do is I'm given endpoints, so I will take n over p points per processor. Okay. Then I will take the coordinates, XYZ coordinates of each point, and turn it into the corresponding bit string representation of its leaf cell. Okay, we just talked about how to do this. You take each of the coordinates separately, divide it with your 2 to the L, take the floor, get the box number, position along XYZ, turn it into bits, and then a bit interleaving. You automatically compute the key for the leaf cell that contains you. Okay, you can do this independently for each of the n over p. Once you do it, you simply sort them using any parallel sorting algorithm. And you can get n log n runtime, and you will get the left to right order of these leaf cells. So you're trying to construct a tree, but you manage to construct a sorted order of the leaves so far. You can spend n log n time, and you can use any sorting algorithm you like, Pythonic sort, sample sort, whatever you like. You can even use radix sort, because if you assume that you're not going to break beyond a certain number of levels, you can even use a linear time radix sort. Of course, you have to use parallel versions of these because we're talking about parallels.
The sorting is global or just local for every processor? It should be global, right?
Yeah, we're talking about a global sorting. So each processor has n over p points, and every point is independently translated to the ID of its leaf box. Then we take all these IDs and we do a global parallel sort. And then as a result of the sort, you again assume that each processor has N over P points, but they are in the sorted order now, right? The usual sorted order, right? Smaller ones will be in P0, bigger ones, slightly bigger ones will be in P1, even bigger ones will be in P2, and so on. And within each processor, the N over P points are ordered. Basically, what you have is a Z-space filling or Morton ordering of all the points at this stage. Okay.
Mm-hmm.
Now, what the algorithm does is that you borrow the first leaf node from your next processor. Okay, so P2 will say, let me borrow the first leaf in P3. P3 will say, let me borrow the first leaf in P4. So independent of the size n, you just borrow the next guy. Okay. So now you have your N over P points and the one borrowed point, right? Your cells and one borrowed cell. And using them, everybody in parallel runs a sequential reconstruction algorithm to construct tree on the points that they have. Okay.
So when I say first leaf, do you mean in a solid order?
Right, in that Morton ordering, right? So every processor has N over P points in ordering, right? So you use your N over P points and borrow the first point from the next guy. So now you have N over P plus 1 point. And you just construct a tree locally without worrying about anybody else for these N over P plus 1 points. But you do that simultaneously in parallel on every processor. And the tree can be constructed in N over P log N over P time, because there is a serial N log N algorithm, which I'm not describing to say so.
So there is so the leaves that is what the processor's leaves should be spatially close to each other, right? Is that correct?
That automatically happens because of the Morton ordering.
Okay.
So the only requirement, the only thing that all processors must agree on is that they all should start with the same domain box size, because the different octaves that different processors are computing will not be compatible unless everybody agrees on the same root box.
But when you give the n divided by p points to each processor, what do you base on?
Right. So the first step in the algorithm is that you would find the minimum and maximum along X, Y, Z across all processors. You can do that using a simple MPI reduce, right? And once you know the span along X, Y, and Z, you can construct a cube which contains all the points and let every processor know about this cube. It's very simple, right? You do an MPI reduce to figure out min and max along X, Y, Z. Then you find X max minus X min, Y max minus Y min, and so on. Take the maximum of that, and if you pick a box of that size, it will fit all the points. Then you just do a broadcast, and every processor will know the box. So the root box is the same, and you construct your trees for your points only with respect to that root box.
So in that case, your processor will just be a subcube of the cube you have.
It's not necessarily a subcube, because depending on where the particles are, you may get a part of a cube and so on, right?
Yeah, that's correct. But again, those leaves that is on one processor should be spatially close.
That's correct. And that's what gives you a good runtime. But you may have portions of boxes of different sizes. So essentially, what you have can be described as a union.
So, Srinivas?
Yes.
That means you're saying that you're not already Morton ordering the cells, the leaf cells, prior to creating the tree.
Yes, that is.
I'm sorry, what is true?
Yes, it is.
I'm sorry, whatever you said got eaten up.
I think that unmute the microphone for some reason. I don't know why that is. But yeah. You have to first sort all the points into the Morton ordering. That's crucial for the parallel algorithm because that will exhibit locality, and as Shula observed, the points that you get within a processor are spatially close.
Yeah, so when you distribute the points to processors, you don't know the ordering. You just know that you basically just have a cube that and basically you assign the points in the cube to different processors, and it's not necessarily in a solid order, right? And then you sort it like in parallel.
Any more questions, Sandhya? Did I answer that question?
Those two answers seem to contradict each other. You're saying that I don't care where the cells are, I initially just distribute the n particles or cells among the processes, and then I sort them, which means that I could have cells that really belong to another part of the tree. They don't have to be spatially contiguous. Your first answer said they did need to be spatially contiguous, and then Shula said you sort, and that is actually how you've laid out this algorithm here, that you sort after you decide which points you're going to look at. I'm not sure which one it is.
Okay, let me answer that. So in the beginning, when you load the particles such that each processor has n over p points per processor, you have no understanding of where these points are. So you end up arbitrarily loading them. So each processor has n over p arbitrary points. The first step would be to do a parallel sort by running a parallel sorting algorithm. Okay? And that essentially rearranges these points so that they are sorted in Morton order globally. Now, it is correct to say that the boxes within a processor, the leaf boxes, are actually ordered according to Morton ordering because we just did that. Now, using that ordering, take your n over p leaf boxes and the first box of the next processor and together locally construct an octree using the same domain for everybody.
So the spatial distribution is random for the processors. That's what you said. You say it's randomly load the points for different processors, right? So
at the beginning, of course, you arbitrarily assign points to processors, but after you sort, there is an order, right? So the ordering doesn't exist at the beginning because nobody gives you an ordering; they just give you n points. So the first one is to load arbitrary points, then you sort, and then you have created that ordering, and then use that ordering to construct the tree.
So, sorry, I'm going to say what I have to say and then get off because it really does seem like I'm creating the echo. That means that it's only in step 3 in this particular PowerPoint that, in fact, step 3 is not working on the same leaf cells as step 1 and 2. Just let me know if that's correct. I'm going to get off.
That is correct. Huh? Yes. So in step 1, a processor has n over p points that are assigned to it arbitrarily. In step 2, every processor uses its n over p points and participates in a global sort, right? There is a total of n things. You do a global sorting. Obviously, the things that you have after sorting are not the same as the things you have before sorting. And then the third step, you have the n over p points that you have after sorting, right? So using those, you construct the local tree.
So there is a redistribution at step 3.
Yes, of course, the sorting is a redistribution.
I see.
Sure, I think the redistribution is actually in step 2. Like you have random shufflings, right? Like you don't each processor have n over p points, but they are not necessarily like what they will eventually get. And then the second step, you do the redistribution. And now at this point, after this global sort, each processor will have the one they will deal with at step 3. And step 3 uses the same points they get from step 2. So it is actually at the global sorting, actually the processor gets the points they will eventually process.
Yeah.
Okay. Yeah, I mean, that's correct. I think he got it right. Okay, I'm moving to the next slide, which is showing. So there are two different structures.
Srinivas, Shola, everyone, Chuan, everyone. I actually have to get off right now. Sorry about that, but I think this is really going really well, and maybe I will catch up with Chuan based on your slides.
Mm-hmm.
I hope that's okay.
Yeah, sure, I can do that.
We can also separate and come back and Tuesday again.
Either one is okay with me. How much further do you have to go?
I don't think I can finish it at the rate right now. We have another 20 minutes to finish up an hour and a half, and we are nowhere close to. So I think I will need a full hour and a half. But I think the key thing is that everybody is completely understanding, so which is very nice. And so maybe we should just stop here and again pick up on Tuesday, and I can finish it during that time.
That's fine with me.
That's okay with me as well.
Great. Okay, let's do that then. And you have the slides, you can take a look at them and be more prepared moving us forward.
Sounds good. And Chiwan, maybe we can catch up later today.
Sure.
Thanks.
Oh, wait, one second. I'll talk to you later.
And that's why I was thinking that if we decide, for example, that Shian and Saminda are together going to build the framework, I was thinking that one good way may be to send him here for a week, and I can spend 2-3 hours every day with them for a week and really architect what we need to do and send him back. And that might be helpful because there are lots of algorithmic details here, and it takes time to understand.
Mike, okay, so my mic's not on. I think the problem will be that Chiwan has responsibilities in terms of TAs and other things here, but we can talk about that offline.
Right. The reason I said this is that I don't think you will have time to, sit and go through every small detail, and that's why I thought that the students who are working on it get a credit.
Yep, I hear you. We should talk about this offline.
Sure.
All right. Thanks. Bye.
Bye.
Thank you. It's very helpful. Thank you.
Yeah, you're welcome. So, so I will, I think, I can continue the presentation, and once the presentation is over, you'll have some idea about what really the framework is all about.
Yes.
But then once we figure out at a high level how to do it, really it's important that whoever is working on it knows the full algorithmic details, because otherwise you can't make the system work.
Sure. I also have a suggestion. Like next time, I guess if we are doing something like the video like this, we can try something called Google Air. It'll automatically record the video so that people have questions can refer to it.
Okay. Sure. Yeah. I mean, whatever you think would be useful, we can certainly do that. Hey, one thing I do have to reschedule for next Tuesday. We have a workshop with General Electric.
Mm-hmm.
They want to look into funding a big institute here at Georgia Tech, and their top level executives are coming. We have a workshop from 1 to 4 next week, Tuesday. And that's a meeting where I have no control over setting up the time.
Okay. I'll let Sandhya know. I think she doesn't know this right now.
Right. That's true. So I can do Monday. Monday I am available.
Mm-hmm.
Or we can do it at the same time any other day. That's also fine with me.
Okay.
So if you want to make quick progress, maybe Monday would be better if you're all free. I only have 11 to 12 on Monday. Pretty much any time right now would work, although it looks like one more meeting might happen, but generally I'm free Monday. Okay. That's a possibility.
Sandhya may need to, I don't know, I think she's right now busy with Aspelas, I guess.
Okay.
But I don't know her schedule. I'll definitely talk to her about this and make sure.
Another possibility is that we can meet and I can just describe the algorithm to you, and then maybe we can bring that later.
That'll work too. Yeah, that'll work too. Sure.
Yeah, but my worry is that if she doesn't know some of the high level details, then she'll be handicapped in terms of thinking about it properly, right? So.
Right.
I have the same issue actually. I'm running the IPDPS conference, and so just sending out all those papers to reviews and so on. So.
Yeah, right. She was talking about reviewers having comments on their reviews they receive. So.
Okay. Yeah, I think her conference is farther along. My conference, I just got the papers, but now the tough work of sending 500 papers to reviewers.
Wow.
So I have a review committee of 280 people. We're trying to get 4 reviews per paper, so trying to do assignments, and that's what's happening.
Yeah. So yeah, I'll definitely talk to Sandhya, and then Monday sure. I'm pretty much all free. I on my side there is no issue. So.
Sure. Yeah. Okay. All right. Thanks.
Yeah. Okay. Thank you. Bye, Saminda.
Bye.
Actually, one more thing. I haven't had chance to look at the source code, like the Bitbucket project yet, because I was working on one of the midterms here, and then I don't really have enough time to look into it.
Yeah, that's fine, Javan. Actually, I need to share with you some diagrams which we actually came up with, the existing one, and some of the things that I was thinking of changing in that code.
Mm-hmm.
Let me just send you those images.
Okay. Also,
it's just an architecture kind of diagram. It's not a huge thing. So anyway.